Okay, so we have now concluded, I guess, Unit 1, we'll call it, in the business statistics course. That was half the chapters that we're going to cover, chapters 1 through 6. So now we've got 7 through 12 for Unit 2 and 3. Unit 2 is going to consist of 7, 8, and 9. And tonight I'm going to be putting out content on 7 and 8, as you can see on the screen. Yeah, without any further ado, let's get to talking about it. So chapter 7 and 8, as you can see, is sampling distributions, and confidence intervals. One thing that I want to kind of go back and talk about is what we have learned thus far and how that's going to prepare us for 7 and 8. So in chapter 1, we learned about data. That was a lot of review. That was a lot of stuff that you may have seen in perhaps a high school statistics course or just maybe in some other classes in general. Essentially essentially review and I guess easy learning. Chapter 2, there was some new stuff in chapter 2, but mainly review. We were looking at a lot of graphs. There was probably some graphs that you had never heard of. The Pareto chart comes to mind. It's kind of a mix of a histogram, a bar graph, and a cumulative line graph. So yeah, there was some new stuff in chapter 2, but mainly real easy, and we kind of coupled that with chapter 1. Chapter 3 was descriptive statistics. That was our mean, median, and mode, standard deviation, variance, coefficient of variation, that sort of stuff. That right now is going to be the stuff that you guys are at, like that's a tool set right now that you have from chapter 3 that you're able to use on the case currently. So hopefully you guys are taking advantage of this kind of downtime with me being sick, and hopefully you've communicated with your case groups. But the descriptive statistics portion is definitely what you could be doing on the case right now, is getting down just those descriptive statistics about pre and post scores for all the different categories, and then getting graphs to correspond with that, and talking a little bit about the skewness. But yeah, please let me know if you have any questions on the case. But yeah, chapter 3, definitely where it's at for where you can get started. I'd love to see you guys get a lot of that stuff done earlier rather than later, because you'll be chasing your tails by the end of the semester if you don't start that now. I promise you that. So I would love to answer any and all questions that you guys have. Just shoot me emails, put them in the discussion board, whatever. But yeah, I'd love to answer questions about that now. Yeah, and I'd love to help in any way possible. Chapter 4. Chapter 4, we got into probability. That was a difficult chapter. That's when the course really starts to ramp up, and we start to learn some tough concepts. We learned Bayes' theorem. We kind of said, hey, we're going to cover Bayes' theorem once, and then let's do it the easy way. Let's do it the way that we just throw everything into a contingency table, a probability contingency table, and then we answer questions by completing the table and then going from there. So that was chapter 4, and we learned all the rules of probability that are applicable for this course. So then we get into chapter 5 and 6. Chapter 5 and 6 were discrete and continuous probability distributions, and we learned discrete and continuous probability distributions. Amongst the discrete, we had just like the general discrete, which was, you have an x value and you have a p of x value, and the p of x values are associated with the x values, and those add to 1, and we calculate statistics based upon those. We also had the binomial distribution. We had the Poisson distribution, and I think that rounded it out for the discrete distributions. For the continuous distributions, we had the uniform distribution, which was the flat one, that was the rectangle. And then we had the normal distribution, which is going to be the most common thing that we roll with going forward here. And the thing that you need to understand the most is the normal. And then we also did the exponential, which I don't think we'll really see much in going forward in the course. But the main thing about chapters 5 and 6 is that we learned how to deal with probability distributions. Okay, and we learned how to kind of work in a universe that we have all of the information. We somehow have a data set, and we somehow know that the distribution of that data set happens to be normal, or it happens to be exponential, or it happens to be Poisson, or whatever. These are like mythical things. Like, this is not something that's ever really going to be the case. Like, if you know that, like, put it this way, if you know that much about a distribution or about a data set, like, why are you studying it? You kind of already know everything that you need to know. The reason that we cover those things is to kind of give you the thought processes and the skill set in order to be able to work with, or to think about the way that you need to be able to think moving forward, so that you kind of have an experience level in order to get into the stuff in 7 and 8. Okay, the stuff in 7 and 8 is sampling, and sampling distributions. All right, so we went through 5 and 6. We learned all these distributions in 5 and 6, but we did that so that we have like a general idea of what a probability distribution is and how we work with it. Okay, now in 7 and 8, we kind of relieve some of the constraints, and we say, okay, let's work in the real world. In the real world, we don't have all the rules defined for us. We don't just know that something is normal. We don't just know that something, we just don't just have all of the data elements of whatever we're working with. Or if we know that all of the data elements are countable, it might be just way too expensive to like run calculations on all the data. Like, imagine like if you were taking the census of the United States, and actually taking a true census where we're looking at every single piece of data. I mean, that would be absurd. You would literally have to survey, 290 million people. And there's no way that the information that you could glean from surveying them, honestly, on any number of topics, would be worth it given the cost of actually running that survey, right? So when they do the census, they actually take a fraction of that, like a small fraction of that, and then they interpret the results of that sampling and the statistics that they run on that sample in order to draw conclusions about the population, because it's more cost effective to do that that way. And it's, as we'll find in chapter 7 and 8, it's actually very you can glean very powerful and very accurate results based on a small number of data points relative to the size of a population. So we get to see this. I mean, this is election season right now, and you kind of see this in election season. You see all these different polls that come out about if Trump or Hillary is winning and whatnot. And these polls, amazingly enough, it's not like they've surveyed 10,000 people. A lot of the time they've surveyed 100 people. But they're able to garner fairly accurate results given the randomness of the survey and given the scientific method of the survey and the sampling. Okay, so that's kind of the point. So 7 and 8, we're kind of taking it into the real world. 5 and 6, we learned a skill set that we think is going to allow us to think in the way that we need to think for 7 and 8. And so now at 7 and 8, we're going to apply some of those, some of that thought process, learn some new tools, and figure out how we can adapt this to move forward. Random sampling. If we select n elements from a population in such a way that every set of n elements in the population has the same chance of being selected, then the elements we select are said to be a random sample. All right, that makes sense. So we're selecting a number of elements from a population, and as long as each element has the same probability of being selected or the same likelihood of being selected, we call that a random sample. In order to select a random sample of n elements from a population, we make n random selections from the population, every element equal chance of being selected. Yeah, that's kind of what I said. Sample with or without replacement. With replacement, place the element chosen on any particular selection back into the population. We give this element a chance to be chosen on any succeeding selection. Okay, so that is as it sounds, with replacement. You choose it, you put it back in the population. There's a chance that it gets chosen again. Without replacement, the exact opposite. So once it's chosen, it can no longer be chosen again. The best way to do this is to sample without replacement, because then we don't have any overlapping, okay? And now we see that the types of sampling, we have probability sampling, convenience sampling, and judgment sampling. Probability sampling is where we know the chance that each element in the population will be included in the sample. This allows us for statistical inferences. Convenience sampling is where we select elements because they're easy or convenient to sample. So that's like volunteer response sampling. That's when the participants self-select. Okay, so you just use a customer service system, and then you get asked to do a survey at the end of the call. It is on you whether or not you want to respond to that. That's voluntary response sampling. So it's convenient. So as you can guess, the people that are going to respond to those samples are people who are just either really, really blown away with great service or just really, really ticked off with bad service. And then judgment sampling is where a knowledgeable person selects population elements. Judgment sampling is probably the most unreliable. We really want to be working with probability sampling in order to facilitate that randomness and in order to be making statistical inferences. 7.2, sampling distribution of the sample mean. Sampling distribution of the sample mean x bar is the probability distribution of the population of the sample means obtainable from all possible samples of n from a population of sample size big N. I'm going to go ahead and read this whole slide, and then I'll kind of explain what it means in layman's terms. In many situations, the distribution of the population of all possible sample means looks roughly like a normal curve. That's important. If the population is normally distributed, then for any sample size n, the population of all sample means is also normally distributed. The mean mu of x bar of the population of all sample means is equal to mu. The standard deviation sigma of x bar of the population of all sample means is less than sigma. Okay, so the standard deviation goes down when it's the standard deviation of x bar. Okay, so what does all that mean in real life? So we have a population of data points or population of elements, okay? And this is saying that rather than us worry about what probability distribution that population is, what we do is we sample it with a number of data elements of little n, okay? And when we do that, say that there's 1,000 elements in the population, and say we sample it with 100 units because that's cost effective or whatever. Now, what we do is we create a new distribution. We no longer are thinking about like the elements of the original population data set as being our data points or as being our distribution, so the 1,000. We think of all of the possible sample means as our data points, right? So if we had n equal 100, there's going to be an x bar associated with that. There's going to be a sample mean associated with that. And we view that as our data point. We view that as our possible x bar in our new distribution. So no longer are we looking at a probability distribution that is about x. We're looking at a probability distribution that is about x bar. So we're looking at what are the possible sample means that we can glean out of this data set. The thing that's really, really important is what we get in these last two, okay? It's important to know that like this mu of x bar, this is an x bar for whatever reason, PowerPoint's not showing it correctly. But the mu of x bar is equal to mu, all right? So nothing changes in that regard, okay? But but that's a good thing. What's really important is that the standard deviation goes down. So sigma of x bar actually is going to be less than just regular old sigma. And so we get a more accurate depiction of what mu is going to be, or when we sample and get an x bar, we actually get a more accurate depiction of what mu is likely to be. Okay, and when we sample, we assume that we really don't know what mu is, and so that's the whole point. We're trying to figure out, well, what's mu, and how much confidence can we have in that, and you'll see that that's what we'll get into. I think it'll become more clear as we get into doing some problems, and that's, as you know, that's generally how I like to teach. I kind of leave it up to you guys, and I want you guys to then kind of climb in the book and read and all that stuff, and then ask me questions if you have questions. But I'm going to mainly facilitate a lot of the problem solving, and then trying to explain the process through the problem solving in order to make it more understandable, because I know a lot of time when you read just this math jargon that it sometimes just doesn't compute automatically. So general conclusion, if the population of individual items is normal, then the population of all sample means is normal. Okay, so that's important to note. So if we know what the underlying distribution is, then we know that the population of sample means is normal. Even if the population of individual items is not normal, there are circumstances when the population of all sample means is normal. And this is what's really important. And this is why I said we're going to be using the normal distribution going forward in this class. That second line is huge, because it's saying that, like, if we have a population of data points and they are exponentially distributed or Poisson distributed or uniformly distributed, that's that for that distribution. Okay, but when we take a distribution of the sample means, assuming that we have a large enough sample, and we'll learn that going forward, assuming we have a large enough sample, the sample mean distribution tends to become normal, which makes it really easy, because normal is one of the easiest distributions that we work with, and it's one of the easiest formulas, and we enjoy using the table because the table is fairly easy to use. Okay, so it makes it so that, like, wow, now we don't have to, like, know this, like, whole plethora of distributions. We just have to sort of know normal, and then we take the sampling distribution, and then everything kind of just becomes normal. And it makes the problem solving a lot easier, because we're not now looking at 5 different tables, we're looking at one table. All right, the mean of all possible sample means equals the population mean. We went through that in the last slide. That is, mu is equal to mu of x bar. The standard deviation of sigma x bar of all sample means is less than the standard deviation of the population. Also in the last slide, that is yes and yes. Each sample mean averages out the high and low measurements, and so are closer to mu than many of the individual population measurements. Okay, so that's important to note. When we're taking x bars, the highs and the lows are being averaged in, and so then this sample mean distribution is not going to be as wide as the normal population distribution. It's going to be a lot skinnier because we're averaging a lot of the values. So these sample means are going to tend to gravitate toward mu. The empirical rule still holds, so within one standard deviation. Man, I don't know why this is showing it like this, but yeah, this should be okay. It looks like I correct it in the following slides. Whenever you see sigma sub x or mu sub x, that's actually sigma sub x bar and mu sub x bar. Okay. For whatever reason, I must have missed that one, but I have it going forward. Okay, so yeah, the empirical rule holds. So if you recall the empirical rule from the last few chapters, that was within one standard deviation of the mean. We have roughly 68% of all of the data points. Within 2, roughly 95% of all the data points. And within 3, 99.73. Okay. Moving on, the properties of the sampling distribution of the sample mean. If the population being sampled is normal, then so is the sampling distribution of the sample mean. We went over that. The mean of the sampling distribution of x bar is mu sub x bar equal to mu. We went over that as well. Okay, and now this is where we get into some new formulas. The variance of, which is sigma squared x bar of the sampling distribution is of x is sigma squared x bar is equal to sigma squared over n. Okay, and then the standard deviation follows suit as well. So sigma of x bar is equal to sigma over the square root of n. So that's just taking the square root of that whole variance formula. You take the square root of that whole variance formula, you get the standard deviation formula. Okay. So this kind of shows and proves that the variance of the sampling distribution, the sigma squared of x bar, is going to be less than sigma squared because we're dividing it out by n. Okay, so it's always going to hold true because we divide it out by the number of data points that we're taking in the sample size. Okay.